remember correctly, this is a hierarchy that I talked about as far as the different types of routing protocol is concerned. So there are basically two categories. One is called intra-AS routing algorithm. Okay, other one category is called inter-AS routing algorithm. Okay, so in intra, again there are two types of intra-AS routing algorithm. One is a link state, or that is called as shortest path first, or the other one is distance vector, that is also called as Bellman-Ford algorithm. Okay, but if I remember correctly, so what a link state follows? A link state follows, there are two types of architecture I talked about in general. If anybody remembers, what are the two types of architecture we discussed in general? With local knowledge, other one is called dynamic distributed with global knowledge. There are basically two approaches so followed in basic. So one is dynamic distributed local approach. What it is? This is this approach. Okay, distance vector or Bellman-Ford is using this kind of approach, dynamic, distributed, and local approach. Whereas, so this dynamic, so distributed and global approach is nothing but the link state or state shortest path algorithm. Okay, so that's why link state routing algorithm is basically so dynamic, distributed, and global in nature, whereas so my distance vector routing algorithm is dynamic, distributed, local in nature. So can anybody remember what is this local, what is this global? So when I talk about local, so if I look back into this diagram, okay, so I have given a diagram here. Okay, otherwise, here. Okay, so now look into here. So if I look into this diagram, so when I say A is connected to B, A is connected to C directly. Okay, that means A has the information initially, what is the cost of going to B, what is the cost of going to C. So this is the local information. Local information at A means it knows what is the cost of going to its immediate neighbors. These are the immediate neighbors. But E and so D are not the immediate neighbors of A. Okay, so that's why if we do not have this information, that kind of information is basically called as a local information. But if A knows what is the cost of going to B, C, D, and E, so then that is called as a global information or global knowledge. Okay, global knowledge means so knowledge of the whole topology. Whole topology. This is the whole topology, complete topology. Okay, complete network. If a particular router is having that information, so then that is called as a global knowledge. If in a network, if you only knows about what is the cost of going to only its neighbors, so that kind of knowledge is basically called as a local knowledge. Okay, so if I look back into this diagram, I mean look back into this concept, so here, so my distance vector or Bellman-Ford equation, so that is following a local knowledge, okay, with the help of dynamic distributed local knowledge, and whereas my link state approach is basically following this dynamic distributed global knowledge. And this is the most popular algorithm that is being used so in the internet as a part of this link state so algorithm. Okay, similarly in the distance vector, so there is a algorithm called so RIP. So that is the implementation, real implementation of this particular distance vector concept in the internet nowadays, RIP. So there are also other algorithms are available, but these are the two most popular algorithms, so which is basically used as a part of this distance vector and link state, which are again a part of intra-domain AS routing. But so again another algorithm is required to make a communication in the internet, that is called as a inter-domain or inter-AS routing algorithm, and the so popular approach that is being followed is the path vector, and the implementation in internet is called as the BGP, that is the border gateway protocol, that we have to discuss in the last class. Okay, so today let's go for the detail of these two algorithms. So we are, as a part of our course, we are going to go for the detail of link state and distance vector. We are not going to talk much about path vector. We are going to give a very high level overview of this path vector algorithm, okay, as a part of our course. Let's go for the so distance vector routing algorithm, how exactly it works. Okay, so as I have already told, it is called as a Bellman-Ford equation. Okay, and also it is a so very old protocol. Okay, distance vector routing algorithm is the so primitive protocol as far as the intra-AS routing algorithm is concerned. As the name suggests, distance vector, so it only so uses the matrix as a, I mean, finding the shortest path, that is the distance. Okay, so it is using the distance. So whoever I mean router is the nearest to me, I should go and follow that path. So that is called as a distance vector routing algorithm, where the Bellman-Ford equation is being used to calculate what is the minimum path or the shortest path going from one location to another location, as I have already told. So this is the RIP, routing information protocol, is the real implementation in the internet as far as this distance algorithm is so concerned. But it is a very old protocol still, but still it is used. It is not obsolete completely, still it is used. Okay, but mostly nowadays, so this is no more used because it is a very simple protocol having lot of flaws. Okay, so that's why this protocol is not so much used nowadays, we can say that. Okay, but still it is in use as far as the real implementation or practical so in network is concerned. Okay, what is the basic idea? How this particular algorithm works? Let's look into this. So as I say, it is distance vector algorithm. Every node is going to maintain a distance vector at its own end. Okay, every node is going to maintain a distance vector. What is a distance vector? Distance vector is nothing but what is the cost of going to its neighbor. Like let's say, for example, if I look into this diagram, so at node A, node A knows what is the cost of going to B, that is 1. So node A knows what is the cost of going to C, that is 5. So this much information is maintained in a table at node A. So that is called as the distance vector. What is the cost of going to so its neighbor C? What is the cost of going to its neighbor B? Along with what is the next stop through which the packet has to travel. So that information is going to maintain in the distance vector. So what is the information maintained in the distance vector? What is the destination? Let's say C is my destination. So what is the estimated cost to the destination? This is the estimated cost to the destination. And what is the next stop? So through which I can go and able to reach C. That is, so if I want to go to reach C, so this is the next stop. So C is my next stop. Okay. So these are the three important information that is being maintained inside the distance vector. So to make a communication possible. Okay. So first of all, each and every node maintains a routing table. So that is with the local information, and that is nothing but called as a distance vector. Okay. And initially only they know the cost of what? Its neighbors, as I have already mentioned. Okay. Then what happens? After, so everybody maintains a distance vector at its own end. Everybody maintains a distance vector at its own end. Okay, what they do, they exchange. Everybody exchange. So the distance vector among each other. Everybody, so now start exchanging this routing table information, that is the local information they have with each other. So then, so whenever somebody is receiving, let's say B is sending its distance vector to A. Whenever A is receiving, so the distance vector information from B, so then how he is going to update it. So own distance vector, that is the main important point we have to understood here. So to calculate the final destination, or so to calculate the route to a particular destination. Okay, that means initially everybody maintains a distance vector. So then everybody going to exchange their own distance vector to each other. So then whenever somebody is receiving the distance vector from its neighbor, then based on the Bellman-Ford equation, so now he is going to find out what is the minimum path going to a particular destination. So after few exchanges, so when everybody is going to exchange their information with each other, after few iteration, everybody knows what is the cost of going to every other node. That is what is the basic idea how this particular distance vector routing algorithm is going to work. Okay, so this is what is written here. So what I have already told. Okay, this is the most important equation we have to understood. So that is, so what I told. So whenever somebody is receiving a distance vector from its neighbor, how he is going to calculate the best path? So based on the Bellman-Ford equation. Okay, what is the Bellman-Ford equation? This is the Bellman-Ford equation. Very simple equation. Okay, so what the Bellman-Ford equation tell that. So let's look back into this diagram to understand this better. So what the Bellman-Ford equation is saying, very simple. So Bellman-Ford equation, let's look into this diagram to understand it. So what the Bellman-Ford equation is saying, let's say, so at node A, we have already maintained, let's look into like this. At node C, let's say node C is at this moment maintaining a distance vector with a information, what is the cost of going to A, what is the cost of going to B. Cost of going to A Cost of going to A from C is 5. And via whom? Via A. If C wants to send a packet to A, the cost of going to it is 5 and via A. Okay. Similarly, C maintains a distance vector at its own end. The cost of going from C to B is 3 via B. Okay, this is the distance vector maintained at C. Now, what is the distance vector maintained at B? Let's look into that. The distance vector maintained at B is like this. What is the cost of going to A? He knows. What is the cost of going to A? What is the cost of going to C? He knows. What is the cost of going to C? He knows what is the cost of going to E. These are the three information available at B because these are the direct neighbors of it. So cost of going to A from B is 1. Cost of going to C is 3. Cost of going to E is 9. Via whom? So as they are one of neighbors, so directly it is the, so next stop is A, next stop is C, next stop is C. This is what is the distance vector maintained initially at the B end. Now what happens? As I have already told, everybody maintains their own distance vector initially. Then they exchange with each other. Now let's say B send this distance vector information to A. How? Based on the distance vector information received from B, how C is updating its distance vector. That is the most important thing we have to understood. Based on what? Based on the Bellman-Ford equation. Okay. Now let's say, so B received this information from C. Whenever B received this information from C, now C, look into previously, C knows that. So what is the cost of going to A? Cost of going to A is 5. Now, whenever he receives this information from B, so what he learns, the cost of going to A is 1 via B. Try to understand this. So cost of going to A is 1 via B. So then what it will do, so now what he knows that the cost of going to, in this terminology, let me learn. So this is dx of y. So this is cost of going from x to y. What is x here? X here is, let's say, C. Okay, X here is C. X here is C. Like this you try to understood. So cost of going to from C to what? Cost of going from C to A. Cost of going from C to A. Okay. So then how to calculate it? Minimum of cost of going to, so C to A. What is the cost of going to C to A? What is the cost of going to C to A? That is 5. At my own end, I have already maintained it is 5. Then, so minimum of this and cost of going from X to B plus B of, so B to Y. Cost of going to X to B. What is B? B is, so right now my B is becoming B because I received the information from, so B at this moment. So now, so my intermediate node becomes the B. So what is the cost of going from X to B? So cost of going from X. Who is X? C. So who is B? Who is B in this case? B. Okay. B is the, okay. Then what is the cost of going from C to B? Cost of going from C to B is 3. Cost of going from C to B is 3. Okay. Then dBy. dBy is D. Who is B? B is C. Sorry, B is B. Then what is Y? Y is A. What is the cost of going from, distance of going from B to A? Distance from going from B to A is 1. Distance of going from B to A is 1. So then on this Bellman-Ford equation, if I go and put what is the final cost of going from, so C to A, so minimum of 5, comma, cost of going from C to B is 3, plus cost of going from, so B to A is 1. So that is equals to minimum of 5, comma 4. So that's why now the new cost of going from C to A is becoming 4. Previously, so what was the information so available at my end? The cost of going from C to A is 5. Now, whenever I receive this information from B, what I learn? The cost of going, so from C to A is 4. Via whom? Via B. So now I should update this distance vector with what information? At C, now I'm going to update the distance vector information for A like this. The cost of going to A is 4 via whom? Via B. This is the new information I have learned from B. So that's why I should update my distance vector based on the received information, or based on the information or the distance vector I have received from my neighbor. If it is whatever information I have received, if through that, if I going to my neighbors, if it is least cost, then I should go and update that information in my table. So if it is not, I should keep my table as it is. Okay, so that is the main idea how basically this distance vector routing algorithm works. So what is the basic idea? Once again I'm repeating. So basic idea is, what is the basic idea? Basic idea, each node maintains a distance vector, okay, at its own end. What is there in the distance vector? In the distance vector, it is having the destination. So destination, what is the cost of going to the destination, and so then via which hop, so it has to go to the destination. These are the three most important information is being maintained at each and every node. Okay, so then after every node has its own initial distance vector information, so after then they go and exchange their distance vector with each other. So everybody is going to exchange this distance vector information with its neighbors. So whenever the neighbor is going to get this information, so based on the Bellman-Ford equation, based on this Bellman-Ford equation, then it is going to update the distance vector or the routing table at its own end. So when it is going to happen again and again, so after various iteration, so then everybody knows what is the minimum cost of going from one node to another node. This is the basic idea how this distance vector routing algorithm works, by using the most important equation to find out the minimum cost, that is called as the Bellman-Ford equation. Everybody got the basic idea, or anybody has any understanding problem in the basic idea, please ask. Then I'll go through an example how to do it. Particular node. So with the help of this exchange of distance vector information. Okay. Let's say I want to calculate at this moment at node C. Okay. What is the final distance vector? I want to calculate the final distance vector or final routing table at the node C. Okay, so for that sake, initially what we know, initially everybody maintains a distance vector at its own end. Look into this is the initial routing table or distance vector at node A. Everybody, because what is the cost of going to A? A is my neighbor, so I know it. So then what is the cost of going to B? B is my neighbor, I know it. So then what is the cost of going to D? D is my neighbor, so I know it. So these are the three information initially available at the node C. Okay, everybody agrees. Okay, so now, what happens now after certain period of time? So now message says, this node A send its own distance vector to node C. So what is the distance vector maintained at node A? So this is the distance vector maintained at node A. Okay, because initially A knows what is the cost of going to B. A knows what is the cost of going to B. That is one. A knows what is the cost of going to C. A knows what is the cost of going to C. And obviously A to A is 0. So not too much bothered about it. Okay. So now these are the two information initially available at A. Now it send this information to C. Now by looking into this information, C is going to find out, can I update my routing table or distance vector based on the information I have received from A? So now let's look into by using the Bellman-Ford equation. So earlier C has maintained what is the cost of going to A is 5. Okay. So from A, it has received this information and it already know what is the cost of going to A, that is 5. So no need to update this information. So this information is not going to be updated. But now if I look into the cost of going to B, initially C knows what is the cost of going to B, 3. So what B is, what this node A is telling me, what is the cost of going to B, 1. The cost of going to B is 1. So now I want to calculate. So via A, if I go to B, is there a minimum path available? Is there a least cost available? So now let's calculate. So my cost is 3. So his cost is now, cost of going from C to A is 5 plus cost of going from A to B is 1. 5 plus 1 is 6. but I already know it is 3. So why should I update? I should not update this information. I'll keep this information as it is. So I keep the information of going to B as it is, that is 3. That was previously available at my end. So no updation is going to happen. Similarly, what is the cost of going to D? Cost of going to sorry. Cost of going to D is 4. But so whenever I receive any information from A, initially A does not know what is the cost of going to D. So I should not update this cost of going to D at my end. So after receiving the distance vector from A, C does not make any updation, because so all the information what is received from A is not going to make a minimum distance to any other node. So that's why it is not going to update its routing table at its own end. So then after certain period of time, now let's say it is receiving a message from B. Now after certain period of time, so now C is receiving a information, the distance vector at B. Okay, so what is the distance vector at B? So that everybody know what is the cost of going to A is 1, B2 0, C is 3, E2 9. So this is the initial distance vector maintained at B. So now it is going to send to send to C. So whenever it is going to send to C, let's see whether there is an update going to happen or not. Now look into here, the cost of going to A. Initially what I know, the cost of going to A is 5. Okay, so now from B I have learned, okay, so from B I have learned the cost of going to A is 1. The cost of going to A is 1. So now I am going to calculate the new cost. What is the new cost? Cost of going to A via B is cost of going from C to B, that is 3, plus cost of going from B to A, that is 1. So 3 plus 1 is 4. Now the new cost from going to C, so 2A via B is 4, whereas initially I know the cost of going to A is 5. So which one is minimum? So this one is minimum. So that's why I update this information. So previously I was maintaining this information, cost of going to A is 5 via A, but now I have learned from B there is a new route available which is minimum, and the cost of going to A is becoming 4 but via B. So this is the next stop. Okay, so this is the destination. So whom I want to send a packet. This is the cost of going to destination, and this is the next stop via I should go through. So that's why what I have learned, what is the new route? So from C to A, the new route is from C to B, from B to A. So that's why the cost of going from C to A is 3 plus 1 4, and who is the next stop? Next stop is B. That important information you must understood here. And how it is possible? Because B send its distance vector to C. That's why by looking into that information and applying Bellman-Ford equation, we could able to get it. Okay. Similarly, the cost of going from B to C to B is 3. It is direct cost, so no need to change anything. So then cost of going to D. Cost of going to D initially I maintain it is 4. Okay, but B does not have a information. B does not have a information what is the cost of going to D. So I will keep it as it is. So now, next one, what I have received, the cost of going to E is 9. Previously, C does not know what is the cost of going to E. That is infinite. So, but now we have learned that the cost of going to E is 9 via B. So that's why what is the new cost of going to E via B? So from C, the cost of going to E is, cost of going from C to B is 3, plus cost of going from B to E is 9. So 9 plus 3 is 12. So the new cost of going to E is becoming 12 via B. So this is the new cost I have learned from B via going to B via, going to E via B. So this is the new information I have learned from whom? So the table that I have received from B node at C node. So finally, now this is my routing table at C after receiving the distance vector from B. So after a certain period of time, again, D is going to send this distance vector information to C. So what is going to happen? See, now let's look into, this is the distance vector at D. So now it is received at C. By that time, C has this routing table at its own end. So now let's look into, after receiving this, is there any updation going to happen at its own end? Let's look into that. So as far as A is concerned, there is no update. As far as B is concerned, there is no update. As far as D is concerned, there is no update. Okay, as far as E is concerned, there is an update. Let's look into, so for E. So what is ln? So what is the cost of going from D to E? The cost of going from D to E is 2. Okay, so then if I calculate, so from now, so what is the cost of going from C to E via D? So cost of going from C to D is 4. So plus 2. So that's why cost of going from C to E via D is 6. But earlier what I learned, cost of going from, so C to E is 12 via B. But now what I have learned through D, so I have learned through D is that cost of going to E via D is 6. That is the shortest path. So that's why I should replace this information with the new information. So this one. So like this. So what the C is updating its routing table or the distance vector at its own end. So from time to time, finally it got the final routing table. So where, so by looking into that routing table, it can say what is the cost of going to A, B, D, and E with the least cost. Are you getting my point? So once every node exchange their particular distance vector routing table with each other, so finally after some period of time, so C could able to know what is the cost of going to each other node like A, B, D, and E with the minimal cost by using the equation. Uses the local knowledge. With the local knowledge, he starts discovering the route. But here the link state algorithm says that no, I will not do like that. First of all, I will collect the global information. So then after collecting the global information, then I will go for what? So finding out the route or calculating the route. So that's why it is. So basically the idea is, so link state follows 2 phases. So in the phase 1, it is trying to acquire the global knowledge. How to acquire the global knowledge? So initially everybody knows the local knowledge. Initially everybody has the local knowledge. He cannot have the global knowledge. So that's why initially every node knows the local knowledge. Then so they exchange the link state information. They exchange the link state information among each other. Okay, every node exchange the link state information with each other. So to know the global knowledge, to have the global knowledge at its own end. Once, so that is happen, how it is happening? Through flooding, reliable flooding. That means everybody is going to, so like the way, so the distance vector is doing, so every node is sending its distance vector to every other neighbors. So similarly here also the link state information is going to pass to every other neighbors. So but that happens, so during, by exchanging the distance vector, they try to calculate the route at the same time, but this did not happen here. So here they just go and exchange the link state information to have the global knowledge, and once they collect the global knowledge, then the second phase starts, where the route calculation happens, or route calculation is being done or carried out by using the Dijkstra's algorithm, so to find out what is the optimal path going from one to another. But what is the most important advantage of this link state routing algorithm? So what I told, somebody has told in the previous class to me, sir, when you talk about the cost, what is this cost? So in distance vector, the cost is always the distance. Okay, but in link state, that cost may be depend on the requirement of the user. And that means depending on the requirement of a network, you can define that cost. That cost may be a reliability, jaise bola tha main. So somebody wants to make a communication using a secure path. So somebody wants to communicate using a non-secure and faster path. In that case, distance may be a factor. But whenever somebody is using a secure path, so in that case, even if that path is a longer path, but as far as my requirement is concerned, that is the best path for me as far as maintaining the security is concerned. So link state algorithm provide that kind of feature where we can use different metrics to find out the cost, minimum cost, not only the distance, but in case of distance vector routing algorithm, it is using the distance as a part of it to calculate the minimum cost only. Okay, that's the basic difference. And so another difference as far as the link state and distance vector routing algorithm is concerned, distance vector is very, very simple. Okay, so but if you look into link state algorithm, as it is implementing lot of different variety of metrics, so the complexity arises as far as link state routing algorithm is concerned. So depending on your requirement, so you may choose a link state routing algorithm to route, or you may go and use a distance vector routing algorithm. Let's say my requirement is nothing to bother about security, nothing to bother about much. I want to just do the communication with a certain distance. So I should go for choosing the distance vector routing algorithm, because this is very simpler, and also it is going to be faster. Okay, so but if we go and use a link state routing algorithm, as it is complex, so it will take some time to process the packets. So that's why, so it is bit maybe slower at certain point of time. So but again, it depends on the requirement or what is your requirement as a part of your communication to decide what kind of routing algorithm you are going to use as a part of intra-AS routing algorithm. Okay, so now these are the basic 2 pages. The first page is reliable flooding. So through exchange of link state information, we are going to collect the global information. Once we have collected the global information, then we have to calculate the route. So this is based on the Dijkstra's algorithm. So let's look into the first page. The first page is very, very important for us to understand how it exactly works. Now let's look into the first page. See what I have told. I have told, so that is each node is going to flood, or each node is going to send its own link state information. So now we have to understood what is there in the link state information, what message we have to send as a part of this link state information. Okay, so that's why in the link state information we are sending a packet that is called as a link state packet. So whenever we are talking about this reliable flooding, so sending the information to its neighbors, so you have to deal with 3 questions. So what message to send? Whenever you send, so we have to send the link state information. What exactly we have to send? We have to know. So then we have to understood. So when somebody is going to, I am sending a message, means somebody is going to receive this message. When somebody is going to receive this message, how he's going to react upon it? Whenever somebody is receiving this link state information, how he's going to react on it? So then, and the third question is, so when to send this link state packet? These 3 questions we have to answer if you want to understood how this link state routing algorithm works as a part of this phase 1, that is by doing the reliable flooding. Let's look one by one. What is the content of a link state packet? Let's look into that. As a part of the as a part of the content of the link state packet. So first of all, the ID, node ID, each and every node must attach its node ID. So while sending a packet to, so that other will know from which node I have received this particular packet or link state information. Okay. Then what is it going to send? So it is going to send the link state of the node. What is the link state of the node? Initially, everybody knows the local knowledge. So that local knowledge we have to send. Like the distance vector information we are passing. Similarly, it is called as a link state information, but it is literally same. You can say that. Okay, so that is the local knowledge, local information everybody initially is having, and that local information. Okay, so what I was talking about. So in the first phase, basically we are going to send the link state information to our neighbors. So what is there in the link state information, link state packet? So first of all, the ID of the node. So then the link state of the node. Link state of the node is nothing but, so it is the local knowledge of each and every node. Okay. Then most importantly, so another information we are going to pass in this is sequence number. We'll say just very, so in the next slide, we are going to talk about what is the use of this sequence number. Okay. So then along with that, we are going to send another information that is called time to live. What is time to live? Everybody knows what is the purpose of time to live. So the same purpose, continue then. So in this information, time to live. So time to live is basically used to make sure there is no looping. Okay, if there is a loop in a network, so due to wrong routing, if the packet is going to loop, so that is going to create unnecessary problem or consume the bandwidth. So unnecessary packet is going to be loop around in the network. In order to remove that packet, so this time to live concept is being used. So for the same purpose, this time to live concept is being used in this particular link state routing algorithm. Now let's look into what exactly, how exactly, so this message is going to send whenever somebody is receiving this message, how is going to react. So what we understood, so what is the content of a message we understood now. The most important information, once again I am repeating, the most important information is the ID of the node, the link state of the node. Link state of the node means, so what is the cost of going to its neighbors, that is the local information. So then the sequence number of the packet and the time to live. So now, so the next question I have to answer is, when somebody is receiving, I send this packet, somebody is going to receive this packet. When somebody is going to receive this packet, how is going to react? Let's look into that. That is very interesting. So let's look into that when somebody is receiving this packet. when somebody is receiving this packet LSP, link state packet, so how he's going to react. So now let's say, so suppose a node X receives this link state packet, so generated by Y. Y has generated link state packet. So now suppose X node receives this link state packet. So then Y it is going to receive. So first of all, it is going to check this condition. So whenever X is receiving, now it is going to check, has it received any information? So prior to this from Y. From Y, has it received any previous information, like previous link state information or link state packet from Y? If it is not, he has not received any information from Y till. So this is the first packet he is receiving from Y. So in that case, he's not going to think anything. He's just going to store the link state packet information. Whatever LSP link state packet is coming, now the complete information he's going to store at its own end as it is. So then start a timer. Why it is starting a timer? So because every information is going to valid only for certain period of time. Okay, so that's why it cannot be stored in the router end for infinite period of time, because you already know. Information may be outdated after a certain period of time. Okay, so that's why, in order to keep the fresh information, so it is always maintaining a timer. That information will be valid for only certain period of time. So that is why, after storing this link state information, it is starting a timer for what? So this link state information will be valid. After that, it is going to flush this information from its own end. Okay, then this is the first condition. So that is X has not received any information from Y earlier, but it may happen. So already, X has received certain information from Y. This is a new information he is receiving from Y. Now, whenever the answer is yes, already previous some information I have already received from Y, and this is a new information I am receiving from Y, then it is going to do a comparison. So a sequence number, I have already told, na? So a packet is containing a sequence number, right? So whatever information he has already stored earlier, he must have stored a sequence number. So that is let's say old sequence number old. That is what is already stored at its own end. Now the new packet who is coming having a sequence number. So let's say call it as a new sequence number. Now it is going to compare whether this new sequence number is greater than the old sequence number. If the new sequence number is greater than the old sequence number, what does it imply? It implies that this is the newest information. This is the latest information. Okay. If this sequence number new is greater than the sequence number old, that means it is a fresh information. If it is a fresh information, I should update the previous information. So that's why I should override the old link state information. Try to understand this. So whenever the sequence number received is greater than the sequence number stored, so that means I receive a fresh information, I should go and update my routing table based on the fresh information. But if it is not a fresh information, it may happen I receive whatever sequence number I'm receiving right now. Okay, that is the sequence number new is not greater than, rather the old sequence number is greater than or equals to the new sequence number. In that case, I should not update. I should discard this packet because this is a old information. It might happen due to wrong routing or a path which is being followed, which is very slow path. So this packet has been following the slow path for some reason. So now this is a older information. Now I'm trying to receive at certain point of time. So that's why if it is older information, what I should do? I should discard that packet because I have already fresh information available at my end. Why should I go and keep the older information? So that's why by looking into this sequence number, I could able to know whatever information I'm receiving at this moment, it is a fresh information or it is older information. If it is older information, you discard the packet. If it is a fresh information, you keep the information at its own end, or you update your link state information at your own end. Okay, so this is why using how we could able to update after receiving a particular link state information from a neighbors, how the receiver is reacting upon it. So depending on the sequence number of the packet, it is reacting. So whether to store it or to discard it. So this is the second part of the reliable flooding. The next, now the question is third part. So when to send the link state packet. That is the last information we have to understand. Now, as I said, it is a flooding. If I go and always flood this link state packet, it is going to create a lot of problem in the traffic. Okay, so that's why we do not send this link state packet every time. so or flood it every time. So that's why there are two kinds of so scenario when I need to send the link state packet. The first scenario is periodic update. So what is a periodic update? So from time to time, as I already told, na, so there is a timer. So that is a aging timer. Na? You start an aging timer. Whenever you are storing information, you are starting an aging timer. That means that information is valid for certain period of time. So once that information is so lost, then that information must be again so propagated so that everybody so knows about each other's so link state information. Na? So that means so from time to time, depending this aging timer, so from time to time, this link state information must be exchanged between the what? So routers so as to get the fresh information. That is why so this is called as a periodic update. How it happens? That kind of update is called as a periodic update. That means from time to time, depending on the aging timer, so the link state information are exchanged among the routers. So that kind of update is basically so that kind of so sending a packet or link state packet as a part of periodic update. So update so is called as a periodic update. So time to time we are updating or exchanging this information so to update the routing table. So but another kind of update is called as a triggered update. What is a triggered update? Let's say for example let's look into this diagram. Let's look into this diagram. Everywhere it is written. Okay, let's look into this diagram. So here, if I look into this diagram, so let's say there is a cost of going from C to A. The cost of going from C to A via B is the lowest at this point of time. Okay, that what C has learned. But suddenly what happens? This link got down. The connection between C and B got down. Okay, or let's say the connection between B and A got down. Let's think like this. The connection between B and A got down. So then the moment the link between B and A got down, the information must be propagated from B to C. That is this link doesn't exist anymore. So you cannot go and send a packet via B to so reach at A. So that's why this information immediately must be propagated from B to A. Na? It should not wait for this information to propagate as a part of periodic update. So immediately this information must be propagated from B to A when there is a link change. Link cost changes at B, so that must be propagated to its neighbors so that they can able to update their routing table accordingly. And this is called as a triggered update. This happens as a part of triggered update. Are you getting my point? So there are two updates. One is called as a periodic update. Every node is going to send their so updates or so routing table information, that is the link state information, to every others, so every neighbors, so from time to time depending on aging timer. But there is another scenario when there is a link cost changes. Maybe a link is down or the cost from so goes from 1 to 2 now, okay, because of some reason. Okay, so that's why in that case also, so that information must be propagated to its neighbors immediately. So that is going to happen through a triggered update. So that's why there are two kinds of updates. So that is going to happen as a part of so this link state routing algorithm. So one is called as a triggered update. One is called as a periodic update. There are two updates. So one is triggered update. So when it is going to happen? When the link state information changes at that point of time. So it is going to be a triggered update. So periodic update. So it is basically as a part of the aging timer, and that is basically in our order of hours. Okay. So maybe 1 hour, 2 hour, depending on the implementation, it is going to be chosen. So what time is a good time so as to so send this periodic update. Otherwise, there will be a lot of flooding and lot of packets will be so exchanging among the routers in the network. So as actual communication may be hampered by that. So that's why this periodic update is going to be using long timers like order of hours. Okay, so this is what is the basic of so the first page. So that is how we collect the global information. So once we collect the global information, so the next stage is the route calculation. So the route calculation is being done by using this algorithm, Dijkstra's algorithm, that you already know it. Dijkstra's algorithm you already know now. So everybody knows so how this Dijkstra's algorithm works. So to calculate the shortest path. So I'm not going to tell much detail about this. So Dijkstra's algorithm. So only so by using this second, once we have understood so what is the I mean, so global knowledge that is acquired at each and every node. So then by using this Dijkstra's algorithm, we are going to calculate the shortest path. This is an example I'm just giving. So this is an example. So how the Dijkstra's algorithm is calculating, just very high level overview I'm telling, because you already know the detail of it. You can do it very easily. So let's look into, this is a diagram of various nodes connected to each other. Okay, so now using Dijkstra's algorithm, how this is calculating the shortest path. We start with a particular node. Okay, let's say U, we start with U. Okay, so then what is the cost of going to, so it's neighbors. So cost of going to V is 2. So cost of going to W is 5. So cost of going to X is 1. And cost of going to Y and Z is infinity, because they are not direct neighbors. Okay, so then he's going to add the next neighbor, which is having the minimum cost. Okay, the minimum cost of going to X is 1, that is from U. So now he's going to add the next node on top of it, that is X. When it adds X, now it is going to recalculate the path. Okay, cost of going from U, so to V via X. Via X, if it is 3, but already 2, so I will keep it. So then going to W via X is 1 plus 3. 1 plus 3, 4. But previously I have 5. So now it is updating to 4 via X. So this is the new route he has calculated. So that is going to, so W, so is 4 via X. Okay. So then, so Y, what is the cost of going to Y? Cost of going to Y, so X does not know. Previously, sorry, U does not know what is the cost of going to, I mean, no, but it's calculating. Okay, so that's why, so it is infinity initially. Now via X, if it is going to calculate what is the cost of Y, so cost of going to Y is 1 plus 1 is 2 via X. And so cost of going to Z, he do not know at this point of time. I mean, do not know means actually, so it is knowing, but it's not able to calculate. So because he has not added, so that is infinite. Okay, so then it is going to again add the next lowest. So next lowest is, so either V or Y. Okay, these are the two lowest. So cost of going from, so U to, so Y or V. One of them can be chosen. Let's say he has chosen Y. He has chosen Y. Okay, once he has chosen Y, then again he is going to calculate the path. So finally he got the cost of going to, so V again remain the same. Cost of going to W. Let's look into this via Y. Via Y, cost of going to W. So cost of going to, so W via Y. So here it is 1 plus 1 plus 1, 3. Previously he has the information, cost of going to, so W via X is, so 4. Now he learned a new information, 1 plus 1 plus 1, 3. So he has updated it. 3 via whom? Via X. So that's why. So this is the cost of going to. And now, so from Y he has learned the cost of going to Z is 2. So that's why now what is the new cost? So 1 plus 1 plus 2, that is 4. So 4 via X. So cost of going to Y, sorry, Z via X is 4. This is a new information he has learned. Similarly, so now he's going to add the next nearest one. So that is V. So he is added V. After adding V, so the cost will remain same. That you can see easily. So the cost remains same. There is no change after adding V. So then the least cost is, so W. So 3, that is W. W is added. So after adding W also there is no change. Then finally Z is added. So that means once all the nodes is being added, so then we are going to stop. So by that time, so whatever final value you got, that is the least cost. That means, so cost of going from U to V is 2 via V. Cost of going from U to W is 3 via X. Cost of going from U, so 2X is 1 via X. Then cost of going from U, so 2Y is 2 via X. So cost of going from U, so 2Z is 4 via X. So these are the least costs that is being calculated by using the Dijkstra's algorithm. After the whole algorithm is over, you got this information. So that is the least cost path going from one node to every other node.